p to the r. So that's the first statement here, where p is a prime, which is the characteristic of the field. So if you take any element and add it p times, then that's going to be 0. So that is the characteristic. And p is the least such integer, and that's always a prime. And so the order of a finite field is of this form, p to the r, that we have seen. That's the first thing we have proved. So we are not claiming here that given a prime and an integer r, we have a field of order p to the r. What we are saying here, that every finite field has order of this form. The other way around is also true, which we would see a little later. The second important proof was this, that the non-zero elements of F is of course a group under multiplication, but interestingly it's a cyclic group. So that's the point. And then we saw a general construction. So if so our first observation was that all these the ring Z mod P is always a field, which we also denote by Fp. Our general notation for a field of element Q, field of order Q, would be Fq. And in that way we are replacing Zp by Fp. So for a prime, it's always a field. And if we have an irreducible polynomial in Fp over Fp, so it's an element of the polynomial ring Fpx. So it's a polynomial with coefficients coming from Fp, and it's irreducible there. And suppose the degree of that irreducible polynomial fx is m, then we can construct a finite field containing p to the m elements. So here again, we do not yet have shown the existence of a polynomial, of an irreducible polynomial of degree, of a given degree. But what we are saying here, that if we have an irreducible polynomial of degree m, we can construct a finite field containing p to the m elements. So in fact, we defined an equivalence relation on this polynomial ring Fpx, and the quotient, the equivalence classes form a field of p to the m elements. In other words, if you just in ring theoretic language, this quotient ring Fp of x, this polynomial ring, quotiented by this ideal, which would be a maximal ideal because fx is irreducible. So that's the ideal generated by fx. So yeah, so this is the ideal generated by fx. So if and that will be a maximal ideal if, because fx is irreducible, and that turns out to be a field, and it's going to have p to the m elements. So we have seen this construction, and the next thing what we saw is, if we have a finite field with q elements, then these are the properties, that every element satisfies this relation, that a to the q is equal to a, which is very clear from the fact that the non-zero elements form a cyclic group of order q minus 1. So for any non-zero element, a to the, so if a is non-zero element, then a to the q minus 1 is 1 for all non-zero element. And therefore you can multiply by a on both sides to get this equality for non-zero element, and it is anyway true for the element 0, both sides being 0. And the next thing is, this is more interesting, I mean more So this is a very easy consequence of the earlier thing, but this is an important observation that x to the q, this polynomial x to the q minus x splits completely in this field f with q elements into linear factors. So this splits completely. In this situation, we say that polynomial splits completely when it can be written as product of linear factor. So this is what we call splits completely. In other words, it splits into linear factors. So all factors are linear. So it cannot split anymore. And f turns out to be the splitting field of this polynomial, x to the q minus x over ap. And that gives us a way of constructing finite fields of a given degree, given order. So just we just continue with that. So now how do we construct? So this is simply a remark from the last one. So now we simply go other way around. So what we saw here, we started with a finite field with q elements, and saw that this polynomial splits completely. And this is a splitting field of this polynomial. So by splitting field, I mean the smallest field where it splits completely. And that's what happens here. So we can simply just reverse the process when we want to construct a field of order of q. So let me just start with that. So of course, a reasonable q is a prime power. Otherwise, we cannot construct a finite field. For if q is not a prime power, we cannot do it, because we know every finite field has order of that form. So it has to be a prime power. So p is a prime. So so we are just turning around that last lemma. So let f be the splitting field yeah, we can write the splitting field, because splitting field is unique. Splitting fields exist and they are unique up to isomorphism. That we are assuming, actually. We did not prove it. So if b splitting field of x to the q minus x, okay, let me just give this polynomial a name, say fx. So we observe that fx has no repeated root. No repeated roots. So f has all its roots. So all the roots of this polynomial q to the p minus x, sorry, x to the q minus x uh, are inside f. And we are also claiming that it doesn't have any repeated roots. So all the q roots are distinct. So how is that true? So that for that we can use a general fact that fx. So we can use formal derivative for this. So I would just briefly mention what is formal derivative. So formal derivative of a polynomial So if fx is given by this uh, equality, so a naught plus a1 of x. So this definition works fine for any field. So suppose this is a polynomial of, or maybe we just change the, because fx we are using, so just change it to something else, gx. So if gx is some x to the n, so an n degree polynomial over some field, then formal derivative g prime of x is defined to be, so just what you would like it to be. So that's the definition. So just to take the derivative as if you are looking at a real polynomial, and then just use that. So use that formally. So this is going to be this is 2 times a2 of x, because x square, the derivative of x square is 2x, and 3 times sorry, a3 x square, and so on, in a to a n x to the n minus 1. So the degree reduces by 1, as we expected, as we expect it to be. So that's just definition. And it's easy to see that gx does not have repeated root in any extension does not have repeated roots in any extension. So the way somewhere it has roots, so in any extension of the base field. So does not have repeated roots if and only if gx and its formal derivative has no common factor. So the GCD is 1. So, so if the GCD, if and only if the GCD is 1. And that's the case here. So because our fx is, so I'll just draw a line to separate this. This is a general fact, so just separate this part. So just separate this. So this is x to the q minus x over fp. This is what we are looking at. Okay, so I should have written it that it's a splitting field of this over fp. That is what we want to do. We want to construct. So we have this polynomial, and what is the derivative? So f prime of x is rather simple. So this is qx to the q minus 1 minus 1. And that's just 1. That's just minus 1. Because q is 0 in fp. Q is just a power of p. So that's just minus 1. So therefore, fx and f prime x has nothing in common. Their GCD is 1, and that would imply fx has distinct roots. Let me write it right below this. So fx distinct roots. So if I take the set of all the roots of this polynomial, so A is an element of the splitting field. So I just collect, so splitting field, F is the splitting field of this polynomial. So it has all the roots. So I'm just collecting the roots. So A to the Q minus A. So these are all the elements of F which satisfies this. And so S is going to be a subfield. S is a subfield of F, subfield of F, subfield of F where the polynomial splits. So, and if X splits in S. So, but F is the splitting field. F is the splitting field. So splitting field is also the minimal field where it splits, where the polynomial split. So they have to be equal. So splitting field of Fx, therefore, and the polynomial splits in S, which is a subfield. So it has to be actually equal to this. So F is a field with on which contains only the roots of this polynomial. So it is a field of Q elements, and that is what we wanted. So we have a field of Q elements by this argument. So what we are doing here is, given a Q, we just look at the polynomial x to the Q minus x over Fp, and then look at the splitting field, and that gives us a finite field of Q elements. So we can do this for every Q as long as we assume the existence of splitting field. With that assumption, we do it. But one important thing we sort of avoided here, which is the connection with our previous construction. So so this construction, so the general construction that we described earlier, so where we constructed finite fields by looking at irreducible polynomials. So if we have an irreducible polynomial of degree m, then we can construct finite field. And of course, a very relevant question there is to find such a polynomial. So given an m, can we construct, or can we get a polynomial of uh, an irreducible polynomial of degree m? So do we have irreducible polynomial of any given degree over Fp? That's the question. So that we bypassed, we bypassed and used the splitting field argument to construct it. So we'll get back to that question actually. So irreducibility is going to be our main theme in next part. So so here what we see is that we can, yes, indeed we can construct, we the finite fields of finite field exists for every prime power. That much we know. That's now theoretically guaranteed. Okay. So with this, we need some more on roots of irreducible polynomial. So we would get into irreducibility. So this subsection can be called roots of irreducible polynomial. So start with a lemma. So let fx be an irreducible polynomial in fq of x. So it's finite field with q elements and the polynomial, the associated polynomial ring. So be an irreducible polynomial Yeah, it's not really necessary to write again this FQ. I'm saying irreducible polynomial, so irreducible polynomial in this ring. It cannot be factored in this ring. And alpha be a root of fx in a splitting field in some extension, be a root of fx in an extension k of fqs. Then for a polynomial in fqx, h alpha is equal to 0. So alpha is root of this polynomial h if and only if fx divides this polynomial. So this division is in this ring, the polynomial ring. So this is essentially a consequence of Euclid's division algorithm. So we'll just see a proof. So the essential point here is that fx is an irreducible polynomial. So we would also, so the first step is to prove that fx is the minimal polynomial of that element alpha. So suppose gx be the minimal polynomial. So minimal polynomial is the polynomial of least degree satisfied by alpha. So suppose gx in the same ring is the minimal polynomial of alpha. So that's the polynomial of least degree, which satisfies alpha. And then fx can be divided by gx, and by Euclidean algorithm you would get some Rx where degree of Rx is strictly less than the degree of Gx, the polynomial you are dividing with Gx. Now f of alpha is so you can just use alpha here. So q alpha, g alpha. So you can evaluate this both sides at alpha. So r of alpha, and f of alpha is 0. F is a root of fx. Alpha is a root of fx. So if alpha is 0, g alpha is 0 because g is the minimal polynomial of alpha. So that would imply that r alpha is 0. But that's a contradiction. That's a contradiction because g is the minimal polynomial unless r is identically 0. So r has to be identically 0 as gx is the minimal polynomial. Minimal polynomial. So if Rx is identical, R is identically 0, so we don't get a remainder. That simply means Gx divides Fx, but Fx is irreducible. So Gx is equal to Fx. Yes, one small point is that it can be up to a constant. Yeah, it can be up to a constant. That is okay. If we start with a monic, if we start with f to a monic polynomial, then that doesn't arise. Otherwise, there can be a constant. So let's ignore that constant. We can just do that. So fx is equal to gx. So up to a constant, fx is the fx is the minimal polynomial. So therefore, fx is the minimal polynomial. Fx itself is the minimal polynomial. Minimal polynomial of alpha. And that being so, uh, we can use this Euclidean algorithm again to show that fx is going to divide gx. Sorry, h of x. So we can just use the same argument. We can divide hx by fx, and then h at alpha is 0. So that would imply that the remainder polynomial would also satisfy alpha, or rather alpha would satisfy the remainder polynomial. Remainder has a degree strictly less than fx, and fx being minimal polynomial, the remainder has to vanish. The exact same argument again. So the exact same argument again would show that fx divides gx, and that's what we wanted. So this is simply an consequence of Euclid's algorithm for polynomials. Okay, so now something even more interesting. So the next lemma, so we again start with an irreducible polynomial, be an irreducible polynomial. Irreducible polynomial over f cube of degree m. then fx divides x to the q was sorry, you have to just make it a bit smaller. So it divides x to the q to the n minus x if and only if m divides n. So if we take an irreducible polynomial of degree m, then fx divides x to the q to the n minus x. So x power, so it's a tower of, so x power q power n minus x if and only if m divides n. So let's see a proof of this. So suppose, okay, so let me move this to the next page. We just don't have much space left here. So suppose fx divides this polynomial. So we have to prove both ways. So suppose x divides this polynomial x to the q to the n minus x and alpha is a root of fx in splitting field of fx over fq. So we are going from this direction to this. So we want to prove that m divides n. So let alpha be a root of fx in splitting field of fx. So it has root somewhere. So just pick one. So fx divides x to the q to the n minus x. Therefore, the alpha is going to be a root of this as well. So alpha to the q to the n, alpha to the q to the n minus alpha is also going to be 0. And that implies that alpha is an element of q to the n. So the finite field with q to the n elements. So therefore, so alpha is inside that. Now if I attach alpha to fq, so this is the, sorry, fq. So this is the field generated by fq and alpha, or in other words, it's the smallest field which contains fq as well as alpha. So that's going to be inside fq of fqn. And alpha, and what we have seen, so fx now we use the fact that fx is irreducible of degree m. So fx is irreducible if q of x irreducible in this polynomial ring, uh, which satisfies alpha, such that if alpha is 0, if alpha is the root of that. So by our previous argument, just the same argument which we used in our previous lemma, fx is the minimal polynomial being irreducible. So is the minimal polynomial of alpha over fq. So that's the minimal polynomial, and therefore this extension fq of alpha, so this is an extension field, so it is also a vector space over fq, and this dimension of this vector space fq alpha is going to be m, and a basis would be this. So this is m, and this 1 alpha squared and all these powers, so alpha to the m minus 1 would be a basis. Basis of fq alpha. Uh, Let me, okay, so if q alpha basis of over fq. So we have, we can now draw the picture of what we have now. So let's use this to draw a straight line. So I have if q, you have this if q alpha, which is sitting inside if q to the n, and this extension has degree m, and this has degree n. So therefore, m divides n. Yeah, so we really don't need the basis, we just need the degree of the extension, and it is inside, uh, and the fact that it's inside fqn. Just make it clearer, if q of n, yeah, and so okay, so m divides n. So we have a necessary and sufficient condition. So we also need to, now we need to prove that if m divides n, then if x divides this polynomial x to the q to the n minus x. So let's see that how it is done. So conversely, let m divides n. So that implies q to the m minus 1 is going to divide q to the n minus 1. And therefore x to the q, okay, it's a power, so x to the q to the m minus 1 minus 1 is going to divide x to the q to the n minus 1 minus 1 in fqx. So this is just expansions of polynomials. So that's easy to see. So with this in mind, so since this polynomial divides this, so every root of x to the q to the m minus x is a root of the other polynomial. So let me just show that. So just multiplied x on both sides. So to include 0 as well. So so every root of this is also a root of let me just write it in single line. Better. X to the q to the m minus x is a root of, so every root of that polynomial is a root of x to the q to the n minus x. So splitting field of x to the q to the m minus x is contained in f q to the n. So if q to the n, we know that this is precisely the splitting field of this polynomial. So it contains all the roots of this. So the splitting field of this polynomial, because every root of this polynomial is x to the q to the m minus x is a root of x to the q to the m minus x. So therefore, the splitting field of this should be inside this one, and splitting field of this polynomial is f q to the m, so that should be inside f q to the n. Now if alpha is a root of So if alpha is a root of now x to the q to the m minus x over fq, then fq alpha, so that gives an extension of degree m. One second. Yeah, no. So no, that's this slightly wrong. So what we are, no, I'm just making a mistake. So what we want to prove now is that this fx, this irreducible polynomial of degree m, that divides this. Yeah. So we started with the fact that m divides n. So we started with m divides n, and m divides n implies that q to the, so finite field with this q to the m element, so fq to the m is inside fq to the m. So that much we have seen. So the splitting field of this polynomial is inside this. So these are the splitting fields that we know from previous lemma. No, this is incorrect. So it's a root of fx. It's a root of fx. So which is an irreducible of degree m. So therefore it gives an extension of degree m. So fq alpha is a finite field with q to the m elements. Therefore, it has to be, so there is only one, because these are, so all finite fields, so are splitting fields. So a finite field with q to the m element is a splitting field of the polynomial x to the q to the m minus x. So so they are all unique. So that's an interesting fact, in fact. So this yeah, so it's a finite field with q to the m element. So therefore, if q is same as if qm, so that splitting field. So by uniqueness of splitting field. So these equalities are up to isomorphism, which is fine for us. Uniqueness of splitting field. So here we again use uniqueness of splitting field. Let me write it. Yeah. And we have already seen that fqm sits inside fqn. So if q of alpha is inside fqn, and alpha is a, and therefore this alpha is a root of x to the q to the n minus x, because every element of this f to the q to the n satisfies this. This is exactly the collection of all the roots of this polynomial, and also, and evidently then it's the splitting field of this same polynomial. And by last lemma, so what we have proved is that so let's just see the last lemma. So this is what we have proved there. So it says if you have an irreducible polynomial fx and alpha is a root of fx, then a root of fx in any extension. So if some other polynomial satisfies, if alpha satisfies some other polynomial, then fx has to divide that. So that's what happens here. So alpha satisfies this polynomial x to the q to the n minus x, and therefore the irreducible polynomial which alpha satisfies has to divide this. And this is what we wanted to prove, so that completes this proposition. And so the interesting thing here, what we are getting is this polynomial is really very special. So every irreducible polynomial divides it. So it just depends on the degree. If the degree of that irreducible polynomial divides n, then it divides it. So now the question is whether the division is can it divide multiple times? Can its higher power divides it? So an irreducible polynomial. So suppose we take an irreducible polynomial fx of degree m. So we know from this lemma, and m divides n, then fx divides x to the q to the n minus x. So can x squared divides it? So that's what is answered in the next lemma. So this lemma says that the division is with multiplicity 1. So so let me state it. So for m dividing n, an irreducible polynomial fx in um, qx of degree m is not a repeated factor so it divides but its square doesn't divide. Repeated factor of x to the q to the n minus x. So how do we prove that? So suppose it divides with higher multiplicity. So suppose fx square divides it, x to the q to the n minus x. So suppose this happens. Therefore, x to the q to the n minus x can be written as fx square into some lx, say lx, some other polynomial. So some other polynomial. So now we have our tool of taking formal derivatives. So let's see what formal derivative gives. So taking formal derivatives. So we take formal derivative of both sides. So q to the n x to the q to the n minus 1 is this is 2 times fx f prime of x lx plus fx square and L prime of x. So left hand side has this q to the n, so this vanishes. This is just a minus 1. And right hand side you have fx common, then 2 f prime of x lx plus fx. So one power has been taken out. So if L prime of x, this is just minus 1. Therefore, fx has to be constant, which is a contradiction. So that's a contradiction. So that's a contradiction. So it doesn't happen. So this polynomial is really very special. So x to the this polynomial x to the q to the n minus x. So every irreducible polynomial of degree m for m dividing n divides it and divides it only once, exactly once. So we can factorize this polynomial in this way. Let me introduce a notation to write it. Let me just write that line as well. So what we saw is this, that every, so this is what we got so far. So irreducible, every irreducible monic polynomial in if qx with degree dividing n divides x to the q to the x to the q to the n minus x with multiplicity 1. So divides only once, exactly once. So we can write it in notation. So that is our main thing what we have proved so far. So let so m of q, this is the set of monic irreducible polynomials of degree m in fqx. So mm of q is the set of all monic irreducible polynomial of degree m in fqx. Then what we have proved so far amounts to this. Let me just write it down. So x to the q to the n minus x can be written as this polynomial. Suppose let's use this notation kx. So it can be written as a product of these polynomials where m divides n. So if we take the product of all irreducible polynomials of degree m for m dividing n, then we get this polynomial x to the q to the n minus x. Because all these polynomials, what we have proved is all these polynomials divides this left hand side and divides only once. So every such polynomial, every monic irreducible polynomial of degree m with m dividing n divides this left hand side exactly once. So it is exactly the product. And we have also taken monic to actually match, so we don't have to put a constant in front. So because both sides are monic. And this actually gives us a way of counting monic polynomials, counting irreducible polynomials. So counting this polynomial. So I'll do that. So let's have another notation. So suppose, okay, let's just write let. So this is an equation which we get from our last two lemmas and whatever we have done so far. So let's just give it a name. Maybe just call it A. So yeah, so just recall that this Mn Q is the set of all monic irreducible polynomials of degree m. So that's the set. And now let's have a notation for the cardinality. So let n, so n is just the count. So in Qm is simply the cardinality. So this is the number of monic irreducible polynomial of degree m. In fact, if Q is fixed, we can drop that as well. In fact, we can use nm to denote this. Okay, so we use just nm in place of mnq if q is fixed. So if there is no cause of a confusion, we would just use mn. So now we compare degree of these polynomial. So we have two polynomials. We equated two polynomials in A. So we just compare their degree. Comparing degree of both sides in A. So what we get on left hand side is very clear, of course, q to the n. So that's the degree. And what do we get on the right hand side? So this kx, so for a fixed m, so suppose m is fixed, then what we get is this kx has degree m, and how many such kx we have. So we are multiplying this mn So the number of polynomial of degree m that we are multiplying is exactly mn, because that's the cardinality. So we are multiplying that many polynomial. So the degree is going to be multiplied by this m in m. So that's the number of factors of degree m. So each has degree m, and this is the number of factors. So that would be the degree of that part. And then we multiply all such things, all such polynomials with m dividing n. So that would be a summing over m dividing n. So with the convention that mq in so maybe here we have q, so we can put q, or maybe drop it. We are already, so q is fixed, so just simply drop that. So this is what we get, and we want to count this in m. So how do we do that? We have to make use of something which is called Mobius function. So a very well-known number theoretic function. I just briefly talk about that. So we need to use Mobius function. So whenever we have a sum over divisors, we will use this technique. So this mu. So let me just describe the Mobius function first. So mu is a function on natural numbers and taking value in 0, 1 and -1, or if you want to write -1, 0, 1. So these are the three possibilities. So mu of n, a natural number. Okay, so mu of 1 is 1. That's just defined that way. And mu of n for n greater than 1, mu of n is, so if you factorize n, so if n is a product of k distinct primes, so distinct is important. So if n is a product of k distinct primes, then this is -1 to the k, and it's the 0 otherwise. So it is 0 otherwise. Otherwise meaning if n is not square free, then it is 0. So if the primes, so you can of course, given an n greater than 1, you can always write it as a product of prime, but it may not be distinct. Might have prime, might be divisible by some prime powers. In that case, it is 0. So we define it in this way. Let me just put a bracket here. So that's how we define. And it has important property. So if you sum over all the divisors of some integer n in natural number, then what you get is 0, 0 if So okay, so if n is 1, then of course you have only one divisor, namely 1, and mu1 is 1, so you get 1 if n is 1. And in any other case, you are going to get 0. So it distinguishes, so this sum distinguishes 1 from all integers, or all natural numbers. So this fact is very easy to check by using prime factorization of n. Now, what we require is Mobius inversion formula. Mobius inversion. So let say f, or f we are using. So h and g be two functions on natural numbers, so just real valued functions. Oh, in fact, yeah, function on n. Uh, Yeah, you can actually take any abelian group in the range, but let's just consider this be two real value functions. So if h of n is d dividing n g of d, so if one function is a divisor sum over the other function for all n, then then you can invert this formula to express Gn in terms of a divisor sum of Hn, where you need to introduce the Mobius function. So you are again summing over divisors of n, but mu of d, that's the Mobius function, and h of n by d. So d divides n, so n by d is again a natural number, so this makes sense. So this is what is called the Mobius inversion formula. It's actually inversion. So if one such function on a natural number is a divisor sum of the other function, then that function also can be expressed as a divisor sum of this the first function. So it's both ways. So we simply use that here. So we simply use that in this. So let's call that B. So this is called B. So what we have here is, so recall B. We have q to the n written as, just let's keep the same notation. Yeah, so it is right. So d divides, let me keep this notation. So d of nd, that was our notation. So just replace m by d. So that was B. So now use Mobius inversion. So Mobius inversion would give you, so you can write it in other way. So now say n, so that you can do for any n. This GD is now we have written it as GN. So that's the function, and that is a divisor sum mu D q to the n by d, right? Because our this h function is just q to the n, so it is q to the n by d. So Mobius inversion gives us this. So what we have is n is 1 over n d dividing n mu d q to the n by d. So we have a formula. We have a formula for the number of irreducible polynomial of degree n. So the number of, so this is what we proved. So just recall what in was. So in was this. This is the cardinality of this set. So which is the set of all monic irreducible polynomial of degree m. Q is fixed, so fixing the field. So what we have proved is the number of monic irreducible polynomial of degree n is equal to 1 over n, then this divisor sum mu d q to the n over d. And this is a small exercise that show that. So just use this to show that in n is greater than 0, it's always non-zero for all n greater than equal to 1. So it is always non-zero. So so that is fairly easy to see. In fact, what you simply need to do is to observe this thing, that q of d is always greater than equal to -1. It can never be smaller than -1 if d is strictly bigger than 1. And of course 1 is 1. At 1 it is 1. So therefore, if d is 1, then what you have is q to the n by n. And then if you take this lower bound -1, then you simply have to show that all other terms adds up to something less than q to the n. So the leading term would be q to the n by n, and you have to show that other things are smaller. So that is, so what does it mean? So it means that given a natural number n, this n is greater than 0. That would mean that now the set of irreducible polynomial, set of monic irreducible polynomial of degree n is non-empty. for every n. So we always have monic irreducible polynomial of a given degree. So given an n, given a natural number n, and of course the field fq, you always have a monic irreducible polynomial of degree n. So this is what it proves. Okay, so I'm very close to the time, so I actually needed one small theorem, so I will probably add it in the notes, and then then you can have a look and we can discuss it later. Rather than doing that now, it would take some time. So I would just add it to the notes. So add it to the notes. That's better. So what we have seen today, let me just briefly summarize. So we have seen uniqueness of this finite fields. That's the first thing, and then the second important thing is this every irreducible monic polynomial divides this special polynomial x to the q to the n minus x with multiplicity 1. So every irreducible monic polynomial divides and divides it only once. And using that, we could prove that we have irreducible polynomial of every given degree over any fq we start with. But that does not allow us to really construct. We could simply prove that the set of monic irreducible polynomial of degree n for any n is non-empty. That doesn't allow us to construct. So that's a different thing. So that requires some other. So that requires more work. And so what I would do in the next lecture is to factorize polynomials. So there are several algorithms to factorize polynomials. So I would do one of them, and we would see some examples of. So that would be my last lecture. So we would concentrate on factorizing polynomials. So I'll stop with this, and any question is of course welcome.
Hello, sir.
Hello. Yeah.
Hello, ma'am.
I think no questions from audience, like participants, sir.
Okay. So yeah, so if there are none, then anyway we have the tutorial to discuss whatever doubt or whatever question is there. And
Okay, sir.
I would share a tutorial, some problems to discuss in the tutorial tomorrow morning. So I'll just write.
Okay, sir.
And then this note as well, because I would like to add one theorem which I could not cover. That would have taken 15-20 minutes more, which is too much. So I would just add that in the notes.
Okay, sir. Thank you very much, sir. Thank you.
You are welcome. You are welcome. So shall I log out then?
Okay,
Yes,
sir.
Okay, sir.
Okay, sir.
So see
Thank
you.
you, sir.
Yeah, see you.
Okay.
Okay. Thank you, sir.
You are welcome.